Welcome to the seventh session of Computational Fluid Dynamics with Mr. CFD. In this session, we will review what we have learned so far. We will examine the capabilities, limitations, and weaknesses of different algorithms and discretization schemes applicable to CFD, specifically in the ANSYS Fluent environment. Let's get started. Here, we can see the geometry that we will use for the simulation. This geometry will be analyzed under different conditions and with various algorithms for pressure-velocity coupling, as well as different discretization schemes. The channel has a variable width with an inlet width of 5 centimeters and an outlet width of 10 centimeters. The length of the channel is 20 centimeters. Geometry created using spaceclaim. The boundary conditions, including the inlet, walls, and outlet, are shown here. The mesh was generated using an ANSYS meshing software, and it is presented here. All the meshes are quadratic, and the mesh is structured. The total number of grids generated is 8 and 577. The simulation is pressure-based and steady in a two-dimensional planar model. We activate the energy equation and choose the laminar model for viscosity. Air is selected as the working fluid in the material settings, and its density is defined with the ideal gas state equation. Also, air is selected in the cell zone conditions. The inlet is set as a velocity inlet with a velocity magnitude of 10 centimeters per second. The outlet is a pressure outlet. The first algorithm we use is simple, with the gradient set to green Gauss node-based. Both density and momentum are second-order upwind. The final residual criteria are set to 2 times 10 to the minus 5. For initialization, the initial pressure is 0, the x velocity is 1 meter per second, and the temperature is 300 Kelvin. The maximum number of iterations is defined as 6,000. Before running the simulation, we add an animation of velocity contours to be updated every 10 iterations. We start the calculation and monitor the velocity during the simulation. After convergence, we check the final velocity results calculated by the simple algorithm. We can reduce the final residual criteria by an order of magnitude and rerun the simulation. Convergence is achieved after 543 iterations, and we save the results in a folder named as Simple 543. Next, we change the pressure-velocity coupling to Simple C and rerun the simulation. This run converges after 373 iterations, showing that Simple C requires fewer iterations. Then we switch to the PISO scheme and specifying two number of correction. Again, we should initialize the simulation and rerun. Convergence is achieved after 322 iterations, and these results are also saved. Finally, we test the coupled scheme, reinitialize, and run the simulation. This scheme converges much faster in approximately 59 iterations. We observe and save the results at each step to compare the efficiency and effectiveness of each pressure-velocity coupling scheme. Let's examine how the density-based solver performs in this simulation with an inlet velocity of 10 centimeters per second, which is a very low subsonic speed. We select the density-based solver and use Rho's scheme as our initial velocity coupling method. After initialization and running the simulation, we observe that this algorithm does not converge to a steady solution and experiences constant oscillations. Next, we try the AUSM method. Similarly, this approach also fails to converge to a steady solution, resulting in persistent oscillations within the domain. In our simulations with different algorithms and schemes, we can delve into the formulations of each algorithm to understand their results. Let's first examine the total iterations required to reach convergence for each algorithm in pressure-based solvers. The simple algorithm takes 543 iterations to converge. Simple C takes 373 iterations, PISO requires 322 iterations, and the coupled solver achieves convergence in just 59 iterations. We can also observe the results each algorithm provides. Starting with simple and moving toward the coupled algorithm, we see an increase in solution accuracy. But why is this the case? As we discussed in previous sessions, the simple algorithm uses the continuity and momentum equations to calculate corrections for pressure and velocity. However, simple assumes certain terms are zero, which simplifies the velocity correction form. Simple C, on the other hand, assumes equality between neighboring pressure correction terms, modifying the coefficients and improving the solution. The PISO algorithm applies correction in two stages. It first calculates velocities from momentum equations and pressure corrections from continuity. Then, it updates velocities in the momentum equation after the corrections, and once more updates the pressure corrections, improving convergence and accuracy. In the coupled algorithm, pressure and velocity equations are solved together rather than separately. By integrating pressure into the continuity equation through mathematical processes, all equations are solved simultaneously. Thus, the pressures and velocities from each step satisfy both continuity and momentum equations. This integration enhances convergence speed, as evidenced by its quick arrival at a solution compared to other methods. Moreover, as corrections and assumptions are applied to refine the mathematical formulation in each algorithm, accuracy improves and iterations decrease, progressing from simple to the coupled algorithm. However, In terms of memory usage, the simple algorithm is the least resource intensive, requiring minimal memory, while the coupled algorithm is the most complex, requiring higher memory allocation to handle simulations. Another observation from our simulations is that density-based algorithms, specifically row and AUSM methods, are not suitable for very low Mach number or low-speed regimes. This is evident from their formulations. Both of these schemes introduce numerical dissipation proportional to the speed of sound or acoustic speed. At low Mach numbers, this dissipation becomes disproportionately large, overwhelming the physical convection terms, which can lead to inaccurate solutions. Rowe's method approximates the Riemann solution, but at low speeds, there's a significant disparity between the acoustic speed and the flow velocity, also known as convective speed. This disparity causes the eigenvalues of the problem to differ by orders of magnitude, making the system stiff and difficult to solve. As a result, convergence can require many iterations, and solutions may be inaccurate or incorrect. In the AUSM scheme, the flux calculation is Mach number dependent. At low speeds, the dissipation becomes less accurate, leading to numerical oscillations. Furthermore, handling cell interfaces at low speeds can be problematic, potentially creating artificial pressure variations and causing convergence issues. For these reasons, when dealing with very low speeds, specifically below Mach 0.3, it's advisable to avoid using density-based solvers. In such cases, pressure-based solvers are recommended for more accurate and reliable simulations. Okay, let's explore the effects of the under-relaxation factors on the simulation. So let's back to the simple algorithm. But in the Controls tab, let's decrease a little under-relaxation factors. So the pressure under relaxation factor is reduced from the 0.3 to 0.2, and the momentum under relaxation reduced from 0.7 to 0.5. And start the simulation. With this setup, convergence is achieved after 555 iterations. We save this one as simple 555 and then return to the Control tab to slightly increase these values. The default was set to 0.3 for pressure, and we set it to 0.4. For momentum, we select 0.9 as the relaxation factor. We then initialize and run the simulation again. This time, you can see that the residuals do not decrease with iterations. And in the graphical results, you can also observe that the velocity is not physical. Therefore, this simulation does not converge and merely fluctuates between iterations, indicating that the simulation diverges. Let's enhance the graphical window and rerun the simulation. Now you can better see how the solver calculates the velocity inside the channel and observe that it does not converge. There is no universal guideline for selecting optimal under-relaxation factors, but we understand some general principles. By decreasing these values, we enhance the stability of the simulation. However, increasing them can lead to faster convergence. If we have trained or established a better initial condition, we can opt for higher under-relaxation factors. Conversely, if our initial condition is far from the expected result, lower under-relaxation factors are necessary. This is because, in the initial iterations, corrections calculated by the algorithms might deviate significantly from the physical reality. As the solution becomes more accurate and assumptions are reduced, for instance from simple to simple C, higher under-relaxation factors can be used. This is due to these algorithms providing more accurate pressure corrections. In general, it's advisable to start with the default values for under-relaxation factors in Fluent. If you encounter instability in the simulation, you can reduce these coefficients slightly to improve stability. Then, we use a higher inlet velocity of 0.5 meters per second with the simple algorithm and default under-relaxation factors. Let's run the simulation with an initial x velocity of 0.5 meters per second, which is the inlet velocity. Here you can see how the velocity changes during the iterations. The result does not converge to a final steady-state solution and just fluctuates, resulting in instability in the free stream of the jet appearing in the channel. For simple C, if we run the simulation with the same setups. However, simple C also does not converge to a steady solution. If we save the result with the name simple C and then recalculate the simulation with PISO, we observe instabilities in the free stream region. We save these results too. Changing the algorithm to coupled and running the simulation, we find that in contrast to the segregated schemes, the coupled scheme converges to a final steady solution and does not show the free stream instability. We save this result as coupled. Now, let's increase the inlet velocity to a higher velocity, for example, 50 meters per second, to ensure that the physics must be seen in the results after the wake region. Running with the coupled algorithm, you can see that even at this high velocity, the simulation should converge to a consistent and steady solution. If we change the solution algorithm to simple and run the simulation after initialization, we can see that the simple algorithm shows very high uncertainty in the wake region. Rerunning the simulation, we observe that the algorithm still exhibits some instability. Finally, for PISO, we check the results, observe improved values, yet it also shows instability in the simulation, and it does not converge to a steady solution, demonstrating the instability phenomenon. Another aspect we can compare among pressure-based solvers is their ability to capture unsteady phenomena. In our simulations, we found that the decoupled solvers, such as Simple, Simple C, and PISO, are capable of capturing unsteady effects in simulations. During iterations, these solvers exhibit fluctuations and do not converge prematurely to a steady-state solution. On the other hand, the coupled solver does not inherently showcase these unsteady characteristics. The reason behind this is the simultaneous calculation of pressure and velocity in the coupled solver. It satisfies the continuity and momentum equations together at each iteration, leading it to converge towards a steady-state solution naturally. In contrast, segregated algorithms update velocity step by step and then correct pressure and velocity, allowing them to reflect unsteady behavior through successive iterations. The decoupled approach ensures that during each step, only continuity or momentum equations are satisfied individually, which accommodates the capture of unsteady phenomena. This suggests that the steady coupled algorithm is less suited for unsteady simulations unless the unsteady form of equations, incorporating time derivatives, is employed. When used correctly for unsteady problems, the coupled approach can deliver highly accurate transient solutions. Now let's increase the velocity to something higher than the speed of sound, such as 400 meters per second, to explore how the pressure solvers can handle this. First, let's examine the simple algorithm and see how it performs. After starting the simulation, some regions show discontinuities in velocity values. It appears that the simple algorithm captures some shocks, but it also shows uncertainty and instability. For the simple C algorithm, let's rerun the simulation. This scheme struggles with supersonic velocities and cannot handle them, causing the flow to diverge. The residuals plot indicates that the residuals increase to very high values. Next, let's see if the PISO algorithm can capture the shocks. However, PISO also fails to capture the discontinuities in shocks, and it diverges as well. Now, let's test the final scheme, the coupled pressure and velocity. Running this simulation with these schemes, the solution differs from what the simple algorithm provides. It captures the shocks generated at the top and bottom sides, creating a normal shock in the center of the channel. Additionally, downstream instabilities do not appear, resulting in a straight flow, and the coupled scheme converges to a final steady simulation. Once the coupled scheme converges, the residual plot stabilizes. Next, let's solve the simulation using a density-based solver designed for high-speed compressible flows, starting with the AUSM scheme. Running this simulation, shocks are generated at the front of the channel and move downstream. You can see how the residuals behave, with oblique shocks showing as they move to the corners. These two shocks create a normal shock in the center of the channel. Overall, the shock system observed with the density-based solver is similar to what we obtained using the couples scheme in the pressure-based solver. However, there is some instability downstream of the normal shocks, unlike in the pressure-based approach. In last scheme, rho, initially a normal shock generates at the channel's entrance and moves forward to the end. As with the AUSM model, after the normal shock reaches the corners, oblique shocks appear. And finally, these two shocks form a normal shock in the channel's center, completing the final shock system. However, there is instability in the shear flow region not seen in the AUSM model. In conclusion, let's review each algorithm, their strengths, weaknesses, and the regimes or flows they are best suited for. The first method is simple, which is a well-established algorithm with good convergence for steady-state problems. It is very memory efficient and works well for low-speed, incompressible flows. However, it suffers from slower convergence and is not suitable for highly compressible flows or transient, unsteady problems. Therefore, simple is best used for steady-state, incompressible, low-speed subsonic flows involving simple geometries. For usage tips, it's advisable to start with lower under-relaxation factors and gradually increase them if convergence is stable, using simple only for simple steady-state problems. The second method is simple C, which offers better convergence than simple, though still slower than the coupled algorithm. It allows for higher under-relaxation factors and is more stable than simple, making it suitable for more complex geometries. However, it is still not recommended for unsteady flows. Its best use is for steady-state, incompressible, and moderate subsonic flows. Next is PISO, which is excellent for transient problems due to its stability characteristics and ability to handle larger time steps. It also performs well with skewed meshes. However, PISO requires more computational resources per iteration compared to simple and simple C. While not optimal for steady-state problems, it excels in unsteady and transient flows, especially in subsonic regimes. A tip for using PISO is to choose an appropriate number of corrections, typically between 2 and 4, and to start with smaller time steps, gradually increasing them if convergence is maintained. PISO is ideally used for unsteady problems. The next algorithm to discuss is the coupled solver, which has the fastest convergence rate among all methods. It is very robust for all speed flows and works exceptionally well for both compressible and incompressible flows. It is especially effective in problems with strong pressure and velocity coupling. However, Its weaknesses include higher memory requirements and being computationally expensive per iteration. Each iteration demands more resources compared to other pressure-based algorithms, and it is sensitive to initial conditions. The coupled solver can be used for high-speed compressible flows, as well as transient, supersonic, and subsonic flows. When using the coupled solver, ensure good initialization and consider the memory requirements. The next method is the row model, which excels in high-speed compressible flows and effectively captures shocks, accurately resolving discontinuities with lower numerical dissipation compared to AUSM. However, it is not suitable for lower speed flows and can be less stable than methods like the coupled algorithm. Its best use is for supersonic and hypersonic flows, particularly in problems involving shock systems. Careful mesh design near shocks and the use of appropriate flux limiters and good initialization are essential for effective use. The final method covered is AUSM, which is excellent for shock capturing and suitable for supersonic flows. It effectively handles discontinuities, but may produce entropy violations and is not ideal for low-speed flows, potentially requiring entropy fixes. AUSM is also a computationally expensive method. Its best use is in supersonic and hypersonic flows with shocks. If I were to recommend algorithms for various flow regimes, for low subsonic flows with Mach numbers less than 0.3, the simple and simple C algorithms can be used for steady problems, while PISO is well suited for unsteady problems. The coupled solver is versatile enough to be used for both steady and unsteady simulations in this regime. For high subsonic velocities, with Mach numbers between 0.3 and 0.8, the coupled solver is preferred. Simple and simple C are possible options but offer slower convergence. PISO can also be used for unsteady cases. In transonic flows, with Mach numbers between 0.8 and 1.2, the coupled algorithm is strongly recommended. Density-based methods can also be used as alternative options, but it's best to avoid using simple or simple C in this regime due to their limitations. For supersonic flows with Mach numbers between 1.2 and 5.0, the coupled solver or AUSM is preferred. Rowe's scheme can also be effectively used in these conditions, but other pressure-based solvers, especially segregated methods, are not suitable. Lastly, for hypersonic flows, where Mach numbers are greater than 5, density-based methods like AUSM and Rowe are recommended. However, the coupled solver can also be used, given careful setup and preparation. I hope this course was helpful to you. Thank you for watching.